everybody. So we should start the session, the plenary session. I wonder, where is everybody? So my name is Thomas Schmidt. I was the first, 5 years ago, the first TPC chair, and I must actually show you this. This is my long-term effect. I mean, 5 years ago we selected these type of USB sticks, and they are still in use here. So that's some things that should be mentioned. So it's my pleasure to introduce someone who's, let's say, on the opposite side. I mean, in earlier days we were only talking about the good sides of computer electronics, consumer electronics, and now we have Dr. Frank Sabath he's talking about the downside, about the electromagnetic compatibility, about the problems with consumer electronics. Frank Sabath is very well known. He's the IEEE EMC Society Chapter Chair, and he worked in this field ever since. He studied electrical engineering in Paderborn and Hanover, got his PhD in Hanover, and he's now working at the research labs of the Bundeswehr, which is the national forces of Germany. So I welcome Dr. Sabath. He will talk about upcoming EMC challenges. The floor is yours.
Thank you, Mr. Chairman, for the warm welcome. It's not only the downside. I will talk about that as an EMC engineer, and we had an EMC session just in the morning. We are happy about that. Any new product comes up with EMC problems, and that keeps us in business. So we should not complain too loud. This is the structure of my talk today. I will start in the past. So if you understand the past problems and how the history developed the area of electromagnetic compatibility, we will get an idea about upcoming challenges that we can think of. So we just discussed that in the EMC session. We do not really know what is coming on the next corner, as we do not really know what's the next technology, but we have some estimates and some warm feelings. So let us start in the past. I will take you on a journey 100 years back, in fact 123 years back. The starting point of consumer electronics. At that time, electricity was relatively new, but radio transmission began to use. So the first radios, first radio sets were delivered to people over the country. We started to use electrical energy to get light on the streets. And the first cars started some kind of electricity. And they all used ground as a return path, and that caused some problems. And the outcome of the problems was this. The Reichsgesetzblatt was a law on telegraphy installations from 1892. And in fact, this was the first EMC law. And there's in paragraph 12 written, as far as possible. So they already know that not everything is possible. An electric equipment must be designed in a way that interference do not occur. Full stop. We have something similar in our present EMC law, but this was coming from 1892 from a German Emperor Wilhelm II. So the reasons for that are shown here. The first one, we have telephones and telegraph around the world, and the first radio sets were delivered, and they used a legal solution for the problems that they interfere with each other. So this was a reason, and when AM radio broadcast, and who's listened to AM nowadays, but at that day it was top-notch, started in 1920s, the radio frequency interference proved a problem. So they could hear any switching on the lights on the street, and they could hear a car far before they can hear the engine, just from the sparks, and the sparks caused some radiation, and the radio said the AM radio was picking up that. So there was some noise there was some interference, and and the consumer as today, didn't appreciate that noise, so there were complaints. In fact, after that law, in 1931, we had 4 million radio sets, so that's already consumer electronics out in the market in Germany, only Germany at that time, and they have a little bit about 7,000 interference technicians, so we call them today EMC engineers. They were active in some sections, and you see that they settled several 100,000 complaints or cases of interference between radios and lights and the ignition of the car. And in fact, they had 130 court decisions on radio interference, and 88% in favor of the radio user. So we already start with this first law to protect the consumer electron, or the product that was delivered to the consumer, instead of doing something else. So this is a far beginning, and the problems, if you look to that in an engineering way, the first problem is power distribution and communication use earth as return. Nowadays in the EMC community we have a joke, what's the difference between earth and ground? Earth is where potatoes grow. So it's a bad idea to use a common return path. Nowadays we have similar problems, as digital engineers do not believe in return currents, but still those return currents cause some problems. The ignition system of cars caused interference, noise, and disturbance of broadcast service, so they really knocked it out. Nowadays we need radars to do that, but this is still the same effect. And the disturbing the broadcast serving was the challenging technology at that time. The industry want to sell that to the customers, so they asked for help to protect it. The general description is here: the noise source and the victim are separated. At that time they are separated, so the radio system was sitting in some house, and the problem was sitting in another room or outside the house on the street, as the car was going on, or the power distribution was running there. So the interference model they developed in that time is that we evaluate the interference by the voltage across an antenna input port of the receiver. So EMC at that time was focusing on an antenna receiving some disturbing energy, and then they evaluated that. And unfortunately, the standardization is carrying this model up to today, and we will see that will cause some problems too. And the other problem is, instead of doing engineering, they did some testing. So the EMC world, starting in that area, was poorly doing testing. They tested if some interference occurs. If not, the product is okay. If yes, you have to do something. That's another problem we discussed today in our session, that this still remains in EMC, that testing is enough. And instead, we need to start with the EMC issues right at the first design stage. So we have comparable results, and we assumed some far field, as we have separated source and victim. And this is a model that still be written in the standard. You have some source here. You have the receiving antenna. You have a distance. The distance is between 3 and 30 meters. Nowadays, as 3 meters, that's the maximum distance you can achieve in your room. I just told the people that if I go back as a student, sitting in my room, switching on my computer, my intention was working on the computer and listen to the radio. The first location I put the radio was immediately on top of the computer. Bad idea, as every time the computer was writing something on the hard drive, I could listen to that. So the maximum distance I could achieve was 3 meters, and in industry the maximum distance between two equipments you can achieve in a plant is around about 30 meters. So that are written in the standard, and we still do the testing like this. So we need large facilities to do the measurement, and the other problem is, at that time they assumed that everything was on ground. So they put the equipment in a typical way here, and they perform the measurement between 1 and 4 meters high. That's also an assumption that in a room more than 2 meters, I cannot achieve, and in an industry environment 4 meters. The open question is, what happens if this device radiating straight up? You will never pick up that energy, but it still interferes with some cables running around. It's a remaining problem with the standardization here. Now we can go on. The model I showed you is going to these pictures that I got from a Dutch colleague, and I still remember that my brother was playing with his electric train, and he used to play with his train and on Saturdays in Germany, on Saturdays between 5 and 7 in the evening. Wonderful idea. He had some electrical, also some sparking at the motors, and it turned out that the tracks he was building in his room, together with the sparking of the engine, was just hitting the first channel of the German television. And you all know at that time, very famous Sportschau. So the neighbor came up and rang and had some discussions with my parents as exactly that was happened. My brother caused some problems with his train that was coupling to the antenna and going down to the receiver, and sometimes it was the famous club was playing there, and important goal, and the neighbor couldn't match that. So the solution was just hooking up some capacitors and shifting the frequency. That's the old solution. But this situation is a situation of the past. If you go out and if you go around the IFER, you see that electronics is everywhere, and this is a situation that we have facing today. This was yesterday. No electronics in an office. Yes, this is more or less today tendency to the past. You see a typical workspace in an office. There are more than one computer. The phone is electronic, and what's more important, we all carrying our cell phones, hoping that they do not interfere with the microphone or whatever. So our workplaces and our living places today are overcrowded with electronics. And 4 weeks ago, we had the major EMC conference in Dresden, and the Volkswagen boss of Saxony was just introducing us to the idea that Volkswagen is going to double electronics in a car within the next 5 years. And that's not the electronics we bring to the cars, that's the electronics that's already built in the cars. If I go around here over the IFA, my impression is the consumer will do the same. So we will put more and more electronics close to each other. And that causes a new kind of problems. And who needs cables? We all want to do that wireless. We are even talking about wireless charging. So we are using the spectrum over and over again. There's a very famous interference problem in the San Diego area, as that one of the gas suppliers used some frequency in the radar band to control the valves. He just hit the air control radar of US ships, and the next US ship that was going into San Diego just opened some valves. Bad idea doing that. So we can search for the electrical objects. This is a present situation, as I showed already explained, that we have an increasing number of complex and electronic systems, and the electronic systems itself becoming more and more complex. And just doing testing, if you take a simple electronic device and ask yourself how many modes or operational modes you can switch it to, and then you want to do the testing for this device itself, you need years, tens of years. Nobody will pay you for that. So just doing testing is not enough. And the model for the testing we do is that they both part of each other. We learned that in medical electronics, the main problem is that doctors tend to put their cell phone on top of that medical devices. So the interference source is in close proximity to the device we have that's a victim. So there is no free field coupling. We have near field coupling now. And every electrical object may act as a source. I'm giving lectures at the university, and I'm telling the students, first thing, there's not a passive part of an electronic device. Any piece of metal acts as an antenna. And any piece of silicon that can switch acts as a source. So if you look to that, we have sources all over, and we have victims all over, and they can interfere in a certain way. So that's our problem. Just an example for consumer electronics. This is a smartphone, and if you look to that, what it is a phone. It is a VLAN PC. I can watch TV on that. I have a GPS receiver, FM radio, whatever you want. We build into that, and they're becoming smaller and smaller, and we are decreasing the power for the signal itself. So disturbing some of the signals is really easy. And what's not written on the right side, this device radiates electromagnetic energy. I'm carrying a source with me that's small, portable, and I might forget about that I have it. So I'm taking this device with me in my car, and if I go on a ride with my family, I have a cell phone, my wife has a cell phone, I have a phone, and the kids too. So we have 4 independent sources in the car interfering with all the electronics of the car. You see, you know that better than I. All these services connected with this small device that we want to use today, and that they should not interfere with the electromagnetic environment. That's a real challenge. And it becomes more and more a challenge as 1 gigahertz. As I finished my PhD, I had a discussion with a colleague. He was with computer industry, and I told him, with your signal frequencies, you might have a problem. As there was a radiation. And he said, no, we have not a problem. The problem is above 1 gigahertz, and standardization stops at 1 gigahertz, so it's no problem. And if interference occurs, customer. Nowadays, we have regulation for that, but above 1 gigahertz, we have a different way of wave propagation. And in fact, our open area test sites are not any longer valid for that testing. We have transient signals with a rise time less than a few picoseconds. I'm working with the military, you just learned, and in 2000, as I started this working, we had some oscilloscope that were able to catch the nuclear EMP, and the challenge there was the rise time of 1 nanosecond, and we had some high expensive oscilloscope there where only 10 units were sold all over the world, and we were the masters of that, owning this oscilloscope. Nowadays, 1 nanosecond is nothing. Consumer electronics will provide you with a picosecond, and the scopes today are able to catch that in a single event. And if you describe the potential, it's not just energy or just not volts per meter. It's the energy amplitude rise time, and one thing is not written here. It's a waveform. We started that discussion also today. The standards just tells you have to use a CW signal with a certain amplitude, but that's not true any longer. If you modify it to a little bit different waveform, if you modulate your CW signal, it might become sensitive less than the normative level. It's just a good fit to your system, and therefore we open a space where you can testing, and then that's not affordable any longer. The other problem is here. It comes from the first they observed it was avionics industry, as usually they are looking to their airplanes as it is a metallic tube. So we all know the Faraday's cage. So if the energy is outside, inside is silence, you can do everything inside without getting any interference. First assumption that fails, which plane is now built out of metal only? So they're using plastics, and that makes it a problem. The other point, if you use a metal tube, and now you're using your cell phone and going into the aircraft, we have a resonant structure, and the energy source is in there, in close neighborhood to some very important electronic devices. So that's one problem. Testing is not really an issue. The next one, we can do it by calculation. So managers like that idea. There's no need for doing testing. You can run some numerical calculation and come back. And if you're working in numerical calculation, yes, you can calculate. You can do some simulation, but you cannot catch all cases that are possible. And then the frequency range above 1 gigahertz, you need to build up a model consisting of so many unknowns that you need a supercomputer and months to do the calculation. That's not acceptable. So we need other models to treat that correctly. The other point is we are now coming over to the risk assessment, what's totally new for the EMC community. In the EMC community, we became more and more used to that there's a source, but we have a standard that limits the source. So there is a maximum radiated power coming from that source, and there's a victim, and the victim has some hardness or some susceptibility. It's also written in the standard, so there's a balance between the source and the victim, and we all comply with the standards, so everything is correct. And if we only look to the standard, I do not need to know anything about my environment. But we have to accept that the standards are written assuming this free field condition. They are not written with some source and equipment working close to each other. They're not written with all these wireless things going on nowadays. And if I do the next step, if there are some criminals want to use electromagnetic energy to interfere with your system, they truly follow the rules that are written. They are doing nothing that's forbidden. So we can now we have to do some risk assessment, and the uncertainties are also written here. The coupling paths are not are unknown, and we just heard that if you go to a bus, not two buses are built in the same way, and we learned it 4 weeks in Dresden that even if you buy a mass product car from Volkswagen, not two cars are built up in the same manner, as the car manufacturers now build in some consumer-specific issues. They are able to do that, so they are not building 100 cars the same way. One car by another has some differences in it, and that makes it's hard for us to predict how they will interfere with your consumer device we bring into that. And the deterministic solution, it's possible, but too expensive. So if you as a consumer electronic engineer ask an EMC engineer, what can I do here? And he says, okay, give me 1 million euros of money and 1 year time, then I will come up with a solution. In 1 year, your consumer device is delivered and nearly go out of the market. So it's unacceptable here. So we need some probabilistic analysis, and this is a new threat. I will not threaten you too much, but that's an upcoming threat. This is a scenario that developed from the military area, but nowadays, if you're not looking to military devices, if you look to consumer devices, and with all the VLAN going on, we have already reports that criminals use electromagnetic energy to interfere, for example, with car security system. So they interfere with the car security system, and then they get all the time to steal the car, or to interfere with security system of jewelry. So they were able to reduce the alarm, or the alarm is not going off, and so on and so on. And now if we go on with the smart homes and smart cities, might be a good idea to interfere with that to open the door. So then the door is open, and the burglar can, the robber can get everything he wants. And the uncertainty here is that we have an unknown thread. There is no standardized thread. We have different types, and we have to accept the opposite side, so that the bad boys are getting smarter and smarter nowadays, or at least one of them, so he's able to build that. The coupling paths are unknown, as we do not know where the cables are running. We do not know, indeed, the behavior of the wireless devices, as the designer is looking only to the intended use of the wireless, and EMC is dealing with the unintended things. And the victim behavior, that's the most challenging part from us. If you say, okay, there's a consumer device, and we talked about that in risk management, we need to know how this device behaves in an unintended way. But usually they are tested if they used as intended. And if I expose them to some electromagnetic field, they might act totally different. Nobody tested that, and in usual EMC tests, we do not look to that. And the problem today is, particular with electronics that build in a large number, the managers tend to get only the CE market and not the knowledge what is going on with the device. So the main intent is just doing some testing, getting some certificates, and then ship it out to the market instead of understand what's really happened with the system. Okay. Now the challenges ahead. I can stop here and can invite you. We go over the International Funkausstellung. The first thing is smart grid and smart city, smart whatever. The problem here is we distributing all the controls, and all systems are communicating with each other. But what will happen if the communication is disturbed? We had a problem we observed a problem at our lab testing a car, doing some intentional electromagnetic interference. Bottom line, we didn't disturb anything, but we caused some false signal in a line running from an oil pressure sensor to the main control of the engine. So the engine control believes the engine is running out of oil, switching off the motor, the engine. We had a smart technician there. He just said, okay, I will restart you. And then the engine control said, no, it's no way to restart the car. The car has to stay here until you fill some oil into that. Go to this environment. Some problem that might be caused here can propagate through the whole network and can cause problems in other parts. If we are able to cause wrong data, the data goes through the system. We distribute it. Now we have distributed sources that need to be controlled and fit to each other. And that needs communication. And if we interfere with that communication, everything might happen. So that was the other part there, the electronic mobility. We have power electronic in the cars, so we are coming back to our origin that the cars are running around with power electronics and causing some interference that might interfere with our smartphone. And I just learned that a couple of months ago, some hacker were able to hack into a car and taking over. And if you go to this driver assistant, I just saw a commercial that was telling the driver that he can step out of he can stop the car on the road next to the parking lot, step out of the car, pushing a button, and the car will do the parking without a driver sitting in the car. That might happen if nothing is there, but just start thinking, what will happen if there's some person is standing by just pushing the phone and causing some interference, and the car is crushing in the car next to them. Who is reliable for that? Who has to pay? And the other problem that's here already for 5 years or longer, most EMI problems do not leave some evidence behind. So the first thing, the first assumption is that the programmers of the car is wrong. If I go back to the old days with first Microsoft products on my computer, whenever I see a blue screen, there was another specific name on my lips. I was blamed for this, but I never thought that some bad guy is using electromagnetic interference to interfere with my computer. Nowadays, I'm not totally sure with that. But I will never comply, say, okay, there was one interference coming from outside, as I do not have a sensor for that. We can go over that as we're running out of time. So the future of EMC problems is, as more electrical devices we are using and as more networks we are using, we are increasing electromagnetic interference, as any cable running will pick up energy. And any transmitter is transmitting energy will causing that interference. And we have to look not only to the unintended interaction. There are some folks out there, they are looking into using that intentionally, and there's no way that a standard or law or whatever will prevent that they are doing that. So we need a technical solution for it, and we have to have that in mind using some risk assessment. We only can come back with a probability that something is going, if something is going wrong, it will not be a catastrophe. So there's no way to provide you with information that your device will work probably in all situations, as a consumer, as the electronic today is too complex to cover all of that. The challenges, it's just a combination of both. We try to do that using numerics and using measurements, but the systems we have in use today, not the future, are too complex for both. So there are more things. If I want to measure that completely, if I want to measure all the whole car on any condition, I need more than a year, and it's too complex to treat it numerically. So we need some combinations, and we have to accept some uncertainties. Yeah, that was just rough overview. I hope I didn't fear you too much. There are some experts out in the area, and they try to provide you with solutions, and they maybe cost sometimes a little bit of money. But anyhow, thank you for your attention, and I'm prepared to take some questions.
Yeah, thank you very much. Other questions? Okay, go ahead. Maybe you use the mic, yeah?
Product safety.
Yes. Thank you, Dr. Sabath, for your interesting presentation. I have 3 points. First point, if we're talking about the future of EMC, what do you think that must be the solution to reduce the level of the source of possible interference, or to increase the immunity of other equipment to intended or not intended source of interference? Which needs to be the way in which the designer, not important if it's consumer electronics, if it's medical electronic, except military.
Yep.
But all other for popular consumption, civilian consumption, what need to be the target? Reduce source or increase the immunity?
Okay. In a perfect world, I would say a little bit of both. If we have, but that's message is out for a long time. If you build a new device, please start thinking if you really need that high data rate and need that wireless communication. However, today I had some pragmatic pills. I know that the reduction of the sources will be not affordable. So the engineering way would be to increase the hardness of the equipment and do some and accept that something may occur and do some risk assessment. If we accept that something can go wrong, we should think about okay, if it is just disturbing of the screen here, I still can deliver the message to you. So that's tolerable. If we talk about the car, there are some systems they should never fail. So we should try harder to make them hard, or at least failure tolerable.
I fully agree with you. Thank you. The way is to increase the immunity of the equipment. Second point, you have used it here, one revolutionary term. You use it, probabilistic risk analysis. What do you mean with the probabilistic risk analysis?
Okay, in this case, we have some uncertainties. One part is if you have something that's larger than a cell phone, for example, a car, we only know that with some likelihood the cable is running on this way. So we have a cable bundle, we have some uncertainties in there. And if we kick that in, we can do some numerical computation or estimation, I will call that. And then it ends up that the system will fail with a certain likelihood. And if you do have that in mind, we can compare the outcome. It's just risk assessment. We can compare the outcome with the likelihood, and then we can assess it. The military way to do it, harden it anyway, but it's coming together with costs, and it's not acceptable for the civil world. But in the civil world, it's acceptable if this is, for example, telling that my students, if I end up with my probabilistic risk assessment that this computer will fail once in 3 years, it doesn't matter to me, as in 3 years I will replace that anyhow. So the effect of, or the outcome of that is that I have to replace my computer. So it's not important for me. I will not spend a single penny or cent to harden that system. On the other side, if the outcome is that some human being will die, I have to do something. So, and attach, not only looking, as the EMC engineers tend to look only at the outcomes, the system will fail, oh, danger, 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 we have to do something. We have to have in mind also the likelihood that occurs or that happens. And if there is a small likelihood, then we have to start to think if it's really necessary to do something.
Okay, if I understand well, in EMC, because the EMC is the country of the functional safety theory, in the father of the functional
I know
safety
that you already familiar with that.
Okay,
idea.
but you suggest practically, and I am fully in accord with you and strongly accept, to use the philosophy which in medical devices, the application of 14971 exactly go in the same philosophy.
Yeah.
Thank you. And for the last point, one suggestion, you have the heart in the right side. Don't go with the smartphone in the pocket in the left side. It's really a danger. It's a threat for your heart, the interference of the level of the equipment.
I switched it off, so that's not a
Okay, but never to not use it in the left side. Thank you.
Do we have other questions? So I would have a question. You were mentioning cars several times as the original motivation for EMC control, and once repeatedly over and over again. I would like you to shed light on something, some different aspect in the cars, in car networks are nowadays actually a victim of this EMC problem, and we have. As we are working in the field, we have this and had discussions in former years here about this too. We nowadays have the problem that actually bandwidth limitations, strong bandwidth limitations come from this. Can you say something? Yeah?
For me, the car is one model of having an environment with lots and lots of electronics in there. If I go over the exhibition here, my impression is in 5 years' time, any household will be acting a similar way. In fact, the cars today become more and more a victim as the car manufacturer putting more and more electronics in there, and two-thirds of that electronics is going just to making the driver happy instead of driving safely. But the problem now is, even if we have bandwidth restrictions, some of the interference, just as we talked about picoseconds, the old way is just do a band filter and some bandwidth restriction and everything is clean. Now, but the unintended interference comes close to our signal bandwidth, so a filter and signal restriction will not help any longer. And the other part is the Lord granted us only a limited bandwidth overall, so we are running out of bandwidth. We are going up to higher and higher frequencies, and in that frequency, the radars are working, so the systems that measure how far is your car from the next car and so on. So we are polluting more and more of our spectrum. But that problem can be easily transferred from a car to nowadays office, next day living rooms, whatever. But the car is a typical case, and it started at the car. I know that there is no spark plug any longer in the car. They're using some modern electronics, but the electronics still receives some electrical energy.
Yeah, supposedly it's quite sensitive.
Yeah, it is.
More questions, comments, remarks?
Complaints.
Here's one.
Right, so you talked about holistic risk analysis. I'm wondering, since I'm not an expert on the field, if there are also approaches, for instance, for monitoring agents, because if one has the model, the electromagnetic model of the device, then some agents may check the current electromagnetic pattern compared to the model to check if it goes really outside and detect attacks, detect peaks, detect something that is going wrong. Is this a possibility?
In fact, I will take your question in a broader sense. In fact, as we spoke here, some colleagues are working on putting together a so-called EMI detector, some device that gives you an idea that your car, yourself, your equipment, whatever, was exposed to a higher electromagnetic field that comes from somewhere. It's not that easy as we talk here, as it depends on the waveform. The other part, usually in present, we are in Europe. It differs a little bit between Europe and the US. In Europe, any device that goes to the European market is tested to its emission. So we test the hardness as well as what is radiated. But it's done only once at one single element. So we do not know what happens if you use that device over a couple of years, and if you modify something to that, it's an issue for a long time, or aging might be a problem here. A regulatory check is not foreseen for consumer electronics. So at the moment it was built the first time, there is some kind of check. I will not talk about how reliable that check is, but there is some kind of check. But after that, nobody else is doing a recheck or a monitoring. There's a monitoring protecting some cell phone frequencies. It's a Bundesnetzagentur in Germany, but they need to get a complaint before they start doing measurements.
So I guess it's time to close the session. Thank the speaker again.
Yeah.